We know an engine is in critical condition when we see it. Thick, turbulent black smoke pouring out of the tailpipe, usually accompanied by a violent shaking sputter from the block itself. When we hook up a diagnostic scanner, the system flags a specific exhaust gas anomaly. It's a digital distress signal from the engine's control unit. But before we trust the computer, we look at the physical evidence. This heavy layer of carbon buildup coating the interior of the exhaust is our first undeniable symptom. Then there's the odor, the sharp, overpowering scent of raw gasoline. Black soot and liquid fuel out the exhaust pipe mean the engine's core combustion chemistry has broken down. To fix it, we have to trace exactly where the internal math failed. Internal combustion requires a highly specific chemical baseline. Oxygen and gasoline must ignite in precise harmony to produce clean power. To burn completely, the engine requires exactly 14.7 parts air to 1 part fuel. When running rich, this drops to 10 parts air to 1 part fuel, overloading the cylinder. Without enough oxygen, excess gasoline is violently forced out as raw, black carbon. Scrubbing the tailpipe won't solve the issue. The carbon is just the symptom. We need to trace the fuel delivery network backward to find the exact component forcing excess gas into the chamber. Modern engines operate on a closed-loop control system. It is a continuous, high-speed cycle of sensing, calculating, and acting. The cycle begins at the MAF sensor, measuring incoming oxygen. Data routes to the ECU, calculating fuel valve duration. Finally, injectors spray the requested gas. It's an efficient but fragile loop. One broken component mathematically guarantees a flooded combustion chamber. Now we have to identify the root cause. We need to determine if we're dealing with a physical hardware break at the output or corrupt electronic data at the input. Let's analyze the output side first. The primary mechanical suspect is a localized failure at the fuel delivery point. This shows the internal mechanism. Over time, the internal pintle valve wears down, or microscopic debris wedges it permanently open. The injector loses its ability to seal, bypassing all electrical commands and passively dripping raw fuels straight into the cylinder. But what if the hardware is intact and the brain is being lied to? That points us to the input side. This MAF sensor is coated by oil vapor and dust, creating a thermal blanket. It misinterprets this insulation, reporting a false massive volume of incoming air. The ECU blindly reacts, flooding the chamber with fuel to match oxygen that doesn't exist. Sometimes the sensor is accurate, but airflow is restricted. A completely clogged air filter creates a severe oxygen deficit, mimicking an electronic failure. Similarly, an exhaust O2 sensor stuck reading a lean condition forces the ECU to continually add unnecessary gas to compensate. Mechanical leaks and electronic lies create the exact same physical symptom. We cannot guess the solution. We have to extract the data to prove it. This schematic outlines the diagnostic flowchart we use to trace the black smoke back to its source. The first step is to tap into the engine's onboard computer to read its internal telemetry. The live data confirms what we suspect. The system throws a P0172 code, verifying it is running too rich. The negative fuel trim data shows the ECU is desperately trying to pull fuel away, but it's failing to stop the flood. This digital scan is a crucial starting point. It proves the computer knows there is a rich condition, but it cannot pinpoint which physical part is causing it. To find the actual point of failure, we have to transition from digital screens to manual, physical engine inspection. Spark plugs act as physical recording devices. Analyzing them maps the internal flooding. 1 or 2 wet plugs indicate a localized issue, a leaking injector. But if all plugs are soot-coated, the entire engine is running rich, confirming a systemic sensor failure. Digital telemetry alerts us to the anomaly. Tactile physical evidence isolates the exact broken variable. Let's assume the evidence points to a single fouled plug. To definitively prove that specific injector is illegally bypassing the ECU, we have to extract it from the engine. We mount it on a laboratory test bench for a leak-down test. We apply highly active fuel pressure directly to the injector, completely severing its electrical current. Without a command to open, it should seal. Instead, we observe a steady, passive drip. The physical test perfectly matches our localized hypothesis. We have isolated the root cause, and we can now move to active intervention. Left unaddressed, unburned gasoline initiates a physical erosion process that threatens the structural integrity of the entire engine block. Raw gasoline acts as a harsh solvent inside a hot engine block. When excess liquid floods the chamber, it rapidly washes away the thin, protective film of lubricating oil coating the cylinder walls. This process is known as cylinder wash. Without that oil film, the steel piston rings are left completely unlubricated. This leads to dry, metal-on-metal friction. The piston violently scrapes the cylinder wall, resulting in permanent bore scoring and eventually catastrophic engine block destruction. Restoring the correct air-fuel ratio halts this abrasive wear immediately, preserving the cylinder walls and preventing total mechanical failure. Eradicating this anomaly requires a multifaceted repair protocol. We secure the hardware first, replacing or ultrasonically cleaning worn injectors and chemically purifying the MAF sensor. Finally, we wipe the ECU's memory entirely, forcing the computer to forget corrupted data and recalibrate its baseline. To keep the loop uncorrupted, we enforce a strict preventative maintenance matrix. This requires changing filters exactly on schedule and completely avoiding cheap fuel additives that dissolve internal rubber seals. The system returns to an optimal baseline. The mechanical threat is eliminated, and the internal air-fuel ratio locks firmly back into its perfect equilibrium. Mastering engine diagnostics requires a dual perspective. You have to trust the mathematical telemetry of the computer while relentlessly demanding the physical truth of the hardware.